For more than 50 years, there has been a mismatch between the technology used to build fiber optic networks and the way traffic flows through them. Network traffic flows are mostly point-to-multipoint, where centralized aggregation points collect traffic from consumers and businesses and connect them with the internet, network applications, and content platforms like music, videos, and business services. But the underlying optical technology only transmits data in point-to-point configurations, with each fiber path needing identical optical transceivers on each end to transmit data. And while hub-and-spoke network architectures are efficient at aggregating and managing traffic, the limitations of point-to-point introduce several inefficiencies, including underutilized transceivers, the need for intermediate aggregation, and expensive truck rolls and equipment when upgrades are needed. With ever higher speed broadband services, the emergence of 5G and new cloud-based services, and thus more endpoints and more bandwidth, these challenges only become worse, making the network harder to manage, more costly, and hindering network operators' ability to deliver new services. If mobile networks were built using point-to-point technology, each tower would need thousands of independent radios, one for every potential user in that area, which would be inefficient, cost-prohibitive, and complex to manage. Instead, mobile networks use a single high-speed radio that broadcasts one signal to hundreds of lower-speed devices at the same time. But each smartphone is only able to pick up the calls and data streams destined for it. Infinera introduces to the industry that same concept in optical networks with XR optics. A single XR optic high-speed transceiver can simultaneously send and receive independent data streams to and from numerous low-speed transceivers at different destinations. This is only possible because of Infinera's pioneering advancements in Nyquist subcarriers, a technology that enables a single optical transceiver to create multiple smaller optical subcarriers. With multi-point optics, a single XR optics transceiver in the hub can connect to numerous spokes, reducing the overall number of transceivers needed by 50%, and immediately reducing capital and operational costs, as well as network complexity. Hub-and-spoke architectures will also become more efficient as each hub port on the network will be more fully utilized. Network operators can also eliminate intermediate packet aggregation devices like switches and routers, as traffic can be brought directly to the center of the network. In addition to reducing the cost for those types of devices, this reduces space, power, and operating costs, while simplifying the overall network architecture and making everything easier to manage. XR optics will be delivered in multiple standards-based pluggable form factors, including QSFPs and CFP2s. These devices can be plugged into virtually any existing equipment, like switches and routers, eliminating the need for dedicated optical transponders. And because XR optics enables the use of high-speed ports to aggregate multiple lower-speed signals, instead of having to buy a large router with lots of low-speed ports in addition to the high-speed ports, network operators can simplify operations and lower costs by deploying more compact and cost-effective routers with only efficient high-speed interfaces. Finally, bandwidth management becomes much easier too. With XR optics, additional capacity can be delivered to an existing or new destination with a few keystrokes or by an automated request from a remote location. And if the capacity is only needed for a short time, bandwidth can be released just as easily and used at a different location. No new hardware to deploy, no re-engineering, and no additional truck rolls. Combine all these factors and operators can expect to achieve a reduction in the total cost of network ownership of up to 70%. With the shackles of the point-to-point model now broken, optical network designers are free to rethink how networks are built. Rethink your network with XR optics. For more information, visit infinera.com/XR optics. Having access to the latest network infrastructure technology is critical to an operator's long-term success. With traditional closed optical networking solutions, where the entire solution is provided by a single vendor, operators are limited to a single innovation source and may miss out on important advancements. This limits options, functionality, and service offerings, and results in higher costs. A shift to open networking solutions is well underway. Open solutions seamlessly integrate the best elements from various suppliers into a unified network. This creates a broader ecosystem of innovators and enables network operators to take advantage of new innovations more quickly. Open optical networking relies on the separation of optical line systems and optical transponders. Line systems are like the highways of an optical network. They require a significant upfront investment, and innovation and change are slow. Transponders are like cars. Models and engines evolve more rapidly, and the next new innovative feature is always right around the corner. With open optical networks, network operators can leverage their existing optical infrastructure and choose the best available transponder with the best optical engine from any vendor to meet the specific needs of their application, whether it is for their metro, long-haul or submarine network. This separation or disaggregation in the optical layer is only possible now, since the development of flexible and intelligent transponders with digital signal processors, or DSPs, that can independently adapt to many different types of line systems. Line systems themselves have also become more intelligent and can now seamlessly manage the optical signal independent of the signal source. Compact modular platforms are a new class of equipment that facilitates open optical networks. These include modular chassis that can accept a variety of sled-based optical solutions, so they can be configured with any mix of open optical line system and transponder functionality to meet the needs of the exact application. These all have native open interfaces and standard data models and integrate easily into existing networks. Internet content providers, or ICPs, first adopted open optical networking principles early in their development, which enabled them to scale quickly and cost efficiently, always using the latest technologies. Today, other types of network operators are following their lead, including providers of consumer and business services. To make the operation of multi-vendor networks easier, open optical networks leverage standards-based management interfaces and data models, including YANG, NetConf, and RESTConf. These standard interfaces make it easier to automate planning, service provisioning, and troubleshooting. Open optical networks give network operators a rich ecosystem of innovations to choose from, resulting in a more cost-effective, scalable, and higher-performing network, and enabling increasingly differentiated services. As an industry leader in open optical networking solutions, Infinera has a broad portfolio of compact modular-based open line systems and open transponder solutions. These can be equipped with industry-leading optical engines developed by our vertically integrated Optical Innovation Center to provide the best performance with the best spectral efficiency. For more information, visit www.infinera.com/open.
Thanks to all of you for the opportunity to be with you here today. We'll switch it up from the last presentation a little bit, which I was listening intently to, and we'll move a little more geeky, but I promise not to take it too deep and try to hit the right level. So, we all have a mission, and in this case, we're living in a world of increased capacity and increased networking demands. And so the purpose and kind of the focus of this presentation was to provide some insights and some thoughts around evolutions in optical networking and where the optical transport network is headed. And the three themes I'm going to hit on here are compact optical systems, embedded optical engines, and the advent of pluggable optical technology, which is also emerging. And there's some new revolutionary technologies that are being pioneered in that space. I want to start off because I know everybody's not familiar with Infinera as a household name. And so I don't want to assume that, of course. And so just a little bit here. The company was founded in 2000. And today we have about 3,000 employees. We're a global company, US-based headquarters, and we have about 1.3 billion in revenue. Our focus as a company is designing, the world's greatest optical subsystems and also the systems, if you will, that those optical engines and that optical transmission technology go into. And that's what our engineers and scientists and physicists and marketeers are certainly living every single day. Most of our innovations and our advances come from something we call our Optical Innovation Center. And today's modern optical transmission technology is not that dissimilar in some ways from wireless technology, where digital signal processing enabled the advent of complex modulation schemes where I can send more bits on a per symbol basis. And that can help me get these higher bandwidths and higher capabilities to the handset. And the same is true over glass and fiber optics. We're living with coherent, dense wave division multiplexing. What does that mean? Multiple wavelengths over a fiber pair or a piece of glass that's in a terrestrial market over land, or in some cases submarine and under the ocean and setting on the bottom of the ocean floor. So how does that technology work and how does it come together? Well, it's a combination of analog optical front end and digital signal processing back end, and then that has to be packaged together properly because we're talking about such high speeds and data rates, like approaching 100 gigabaud as an example. And I'll show you a little bit of that here in the next few slides. So where do we do this, and a little bit of how we do it? Where does the Optical Innovation Center live? Well, Infinera is a little bit unique in that we have an indium phosphide fabrication and foundry facility as part of the company's capabilities, and that's been there a long time. In terms of, that was kind of at the heart of the company's founding, was this idea that we want to be deeply vertically integrated and we really want to control the key aspects of this optical engine technology. So in addition to designing the technology, we also have photonic integrated circuit and indium phosphide, which is wafer type technology that you build optical components onto. We have that in Sunnyvale. Our digital signal processing team home is anchored in Ottawa. And then we bring that analog front end and the digital signal processing technology together in Allentown, Pennsylvania, where we have this high-speed packaging capability to ultimately create what we would call our infinite capacity engine, which is a module that gets placed onto a sled or a circuit board. Before we dive into compact, embedded, and pluggable, let's just take one step to level set, the network and the purpose of the network. The reality is we are here as a transport network to do what? We're here to connect people and applications to the cloud and to each other. That's why we exist. And there's no services, whether it's streaming video or mission critical, communications. Those services ultimately ride on a transport network, and that transport network is generally underpinned by optical transmission technology like we're talking about here, which is coherent dense wave division multiplexing that underlies the other aspects of packet and services on top of that. So we said at the beginning of this, we were going to talk about three key themes from where is this industry headed. And those three key themes are an evolution in compact modular optical platforms. The second theme is we're in this kind of fifth generation wave of technology. People would refer to it also as 800 gig technology. That's because a single wavelength over a piece of glass can transmit 800 gigabit per second at a considerable distance or reach. And these optical engines are tunable such that we can dial down that baud rate and that bit rate from 8 to 7 to 6 and even smaller increments as we want the distance to go further and further. So they're really programmatic and they're really tunable in this 5th generation. And again, we've got an analog front end and a digital signal processing back end, and that gives us this tunability and, all vertically integrated and designed by one company here, in this case, Infinera. The third leg of the stool here is this revolution in coherent pluggable optics. With Moore's law and transistor densities getting better, and even though maybe Moore's law is dead, from every 18 months we double the transistors, we still see increases in density and capabilities. We went from, today's technology is 7 nanometer DSP technology. We're on a journey to 5 nanometer and 3 nanometer. And so those things continue. And so let's hit all 3 of these key themes. So compact modular optical platforms, some of this began with kind of the web scale companies designing to create almost appliance-like devices that they were used to from a server perspective, but applied to optical networking. But today's evolution of that, and compact modular platforms have NEBS compliance. They support 300 millimeter depth and 600 millimeter depth for different size racks and office applications. They have replaceable fan, replaceable power units. They have redundant controllers, and they have this modular sled-based architecture that really lets you mix and match the functionality you want, from transponders to switching to the optical layer itself that is amplifying or combining the wavelengths to send over the glass. On the software side, there's been a lot of work in the industry around open interfaces and standard data modeling. What's that about? That's about ease of integration into all kinds of different software environments. And the more we kind of standardize the way you get access to this information, whether it's programming down or telemetry up, the easier it is for us to insert new generations and new products. And that's really where kind of this compact modular platform evolution is headed. In addition to that, modern platforms like our GX series also support this idea of embedded optical engines. Embedded engines typically higher performance, and you see in the long haul and the submarine and into the metro space as well, higher performance, but also bigger size and more power. But they also support the pluggables technology in smaller form factors like CFP2 and QSFP-DD, those kinds of packages that you can hold in your hand, and you've seen plugged into various telecommunications devices. So we've evolved compact modular platforms. We've also designed them to support a combination of pluggable technology and embedded optical technology, depending upon where in the network and the performance and the fiber scarcity, as to if we need to eke out that last bit of performance, or we're fiber rich and maybe we don't have to, and so we don't have to have the leading edge of performance. Infinera's Optical Innovation Center and our latest technology we call I6 for Infinite Capacity Engine, 6th version. We have a number of pieces of intellectual property that make this performance in real world networks happen at an amazing reach versus prior generations. As an example, the Maria cable that goes between the United States and Europe, we put our I6 technology on that network, on that fiber submarine network, and we were able to deliver 650 gigabit per second with deployable margin at over 6,500 kilometers on a single wavelength for a total fiber capacity of 28 terabits over a fiber pair. We also tuned that and cranked it up a little to get 700 gig or 30 terabit per second over a piece of fiber, fiber pair. That was what we would label a hero experiment, and with certainly less or virtually no deployable margin. So I just wanted to set an example of kind of what is it we're expecting from this technology. One of the key things underlying this is because of this digital signal processing combined with analog front end, we have something called Nyquist digital subcarriers, which is this. Instead of sending a 96 gigabaud stream as a single 96 gigabaud stream in a single wavelength, we actually can subdivide that in the digital domain, or we'll call it frequency domain as well, but in the digital domain. And with that, we can send 8 12 gigabaud subcarriers in that wavelength. And it turns out that's beneficial. It's beneficial because we reduce chromatic dispersion and we eliminate some of the nonlinear effects that happen as we crank that baud rate up, and we try to accomplish that all with a single stream of traffic. It's an important point because we're going to make use of that in just a second when we get to the pluggables technology. So let's just take a look at and we'll move off this quickly, but here's the prior generations of technology in coherent dense wave division multiplexing, which began at the 100 gig per wavelength era and is now at 800 gig per wavelength, 5th gen. But just take a look at these distances for a minute. 800 gig at 800 kilometers. We've already talked about a little bit of that. But now let's do a Gen 4, Gen 5 comparison or a Gen 3, Gen 5 comparison. Take a look at how far you could send the top or the max rate of these prior technologies. 400 gig went 300 kilometers and 600 gig went 150 kilometers. Now fast forward to 5th generation technology where 600 gig is 2,700 kilometers and 400 gig is virtually anywhere except for, Pacific subsea links, which might be 10,000 kilometers. So what a significant step forward in terms of transmission ability per wavelength that we see in this 5th generation technology, which is now commercially available and hitting the market. I'm going to pivot from compact modular embedded engines, and now we're going to talk about pluggables for just a second. And so from a pluggables technology perspective, this Nyquist subcarrier was present, and it's been in our systems, but it's hidden, if you will. Well, what if we took these subcarriers and we were able to expose them and assign them to independent destinations or addresses? Well, you would create something from a technology perspective that's been called XR optics. What does that mean, and what could you do with it? Well, if I had 16 of these subcarriers and they each ran at 25 gig, as an example, I could have a 400 gig optic able to talk to a bunch of different 25 gig destinations, 16 of them to be exact. And what I could do is have a high speed 400 gig now talk to a low speed 25 gig or 100 gig optic. We've never done that before because instead we bookended everything. A 10 gig talks to 10 gig, a 25 to 25, 100 to 100, a 400 to a 400, and we had to have the same speed transceivers on both ends of the connection. That's the left picture. What do we do when we want 400 gig here and we got a bunch of 25 gigs over here? We put an intermediate aggregation switch or router in that picture, or a transport device with packet functionality, and then we terminate these lower speeds, we send it back to the electrical domain, back to the optical domain, and then we transmit it at 400 gig on the right-hand side. What if we could eliminate that intermediate electrical aggregation and instead have these subcarriers talk to the higher speed optic? Answer, we could drive down the network cost significantly and make it more flexible. Let's take a quick picture here and take a look. So we have, in that case, we would have, sorry, one more back. If we had 20 interfaces, we'd have 40 transceivers, and we'd still have this intermediate aggregation. With XR optics, We can eliminate that intermediate aggregation. We can almost half the number of transceivers in +1, and we could get this 70% reduction in network performance. Where could I apply this? I could apply this technology to all the kinds of places where I have low speed wanting to aggregate into high speed. That includes, think about 5G radios that need to backhaul back to the disaggregated unit or the centralized unit. Think about 5G transport, high speed, and even high speed broadband, or even PON overlay, where you could do an overlay of this technology on the existing residential infrastructure for enterprise services. We know that XR optics will take more than just Infinera, and this technology has been launched into something called the Open XR Forum, which was literally just announced this week at the OFC conference, and a list of service providers and companies have joined, and we expect others to do so as well. And this is a multi-source agreement style consortium that is meant to bring this point to multi-point and XR optic technology to life across the ecosystem, because we know that is needed. Let's wrap up right where we started, which was, how are we going to accomplish our capacity growth mission with an intelligent optical underlay to support connectivity of people and applications to the cloud? Answer. At least 3 pieces of the answer. We have advanced embedded optical engines. We have this revolution in kind of pluggables technology with point to multi-point functionality that can simplify the network and drive down costs and less equipment. And finally, all of that goes into compact modular optical platforms that support easier integration from a software and a combination of pluggable and embedded optics. And with that, I thank you very much for your time, and thanks for giving me the opportunity to be with you today.
Sorry, I had to take myself off mute there. Tim, thank you very much. And I'm afraid we are at time. We're a little bit over, so we're going to have to break there. But I did just want to sort of throw out something that a CIO said recently, which was, you can't have telework without telecom, and thinking about the connectivity that needs to go into the modern era. You did a great job of explaining some of the sort of the hidden plumbing here, and how we can apply it. So I really appreciate that, and I hope we can pick up this discussion again soon.
Love it. Thanks a lot, Troy.
Thank
Great
you
to be
very
here
much.
with you. Thanks, man.